Morning. Coming to you this morning from the ice planet Hoth. We are going to continue our discussion of multiple sequence alignments. Let me just share my slides with you. These slides are up on the Google Drive folder, topic 3B, part 3. Progressive and iterative approaches to multiple sequence alignment. You remember in the previous lecture, we talked about something called the SP-min method, or the sum of pairs minimization method. That's a somewhat intuitive approach and yet fairly cumbersome and gets very slow for large alignments. So we need a better way. This topic, we are going to discuss some of the more common multiple sequence alignment methods that are available now. And at the end, we'll have a short activity for you to go play with some of those methods. So, approach 2, we call this the progressive method. Examples of this method can be found in software programs like Clustal W or T-Coffee. It works something like this. Again, we start with some number of sequences n. Those n sequences can be arranged into n choose 2 pairwise alignments, and we talked last time about how to calculate that n choose 2 using factorials. In the progressive method, those n choose 2 pairwise alignments are arranged into a distance matrix. This is essentially a grid of distances between all pairs of alignments. This distance matrix can be used to construct what's called a guide tree. We'll see more about what a guide tree is in the next slide. It's important to note here, though, this is not a phylogeny. Although it looks like a phylogeny, it's not. In order to calculate a phylogeny, we generally use multiple sequence alignments. And of course, we don't have an alignment yet. So this is much simpler than a true phylogeny. We call it a guide tree, and it's based on the absolute distances between sequences, taking nothing else into account, such as substitution rate, etc. This is a crude estimation, but in our case, it's useful to guide, hence the name, guide our multiple sequence alignment. It guides us by providing a start or a seed pair. And this is the pair that is closest together in our guide tree. So we use the tree to select the first pair. That is the seed of our multiple sequence alignment. We can then add the next closest sequence. From there, we add the next closest sequence, lather, rinse, repeat until we've added them all. So for example, in this small snippet here, we might start with sequence 5 and sequence 6 as being closest to each other. Then we would add sequence 4, then perhaps sequence 3, then sequence 2, then sequence 1. So the core concept of this progressive method is that those two sequences that are closest together distance-wise are going to be the best aligned. And we can use that to start our alignment. We finally end up with our multiple sequence alignment. And we saw examples of what these look like in the first introduction lecture. So getting back to our guide tree, what is this guide tree and how do we calculate it? Well, as I said, it's based on a distance matrix, which is essentially a XY grid of all sequences and their distance between each other. Then we represent that matrix as a tree. How do we do this? Well, we often calculate using what's called the least squares method, and the formula is here. It looks a little bit cumbersome. It's a sum of a sum, but we're summing up over all pairwise. So I would be one sequence, J would be the second sequence. We're summing up the distance between those two sequences as we observe them. So in the actual grid itself, and how they appear in our tree. And so constructing a guide tree requires us to make a tree. Then we look at the distances that the tree predicts and compare them to what the actual distances are in our matrix. This W here is called a weight. We don't have to talk too much about the weight, but we can provide some context to our distance tree if we want to, using the weight values. But at its core, the least squares method gives us an estimate of how closely our tree represents our distance matrix of actual values. So the distance between two sequences in the tree is calculated by summing the branch lengths between them. So in this case, the distance between sequence 1 and sequence 2 would be 3 plus 2 is 5. The distance between sequence 6 and 5 would be 1 plus 1 would be 2. Okay, so we estimate the tree type topology by minimizing Q, this least squares method. We want the minimal amount of daylight between our tree estimation and our actual grid. Now, as you might imagine, having more sequences than 2, sometimes we have to balance whether we make 2 sequences a little farther apart or closer together, and that may change how they are in relation to other sequences, and so it can be a bit of a juggling act to get it. And we don't often get the perfect tree. In fact, we almost never do, because we have to balance these off. We actually use distance matrix methods like this in estimating phylogeny for very closely related sequences. There are some algorithms out there that we use to do that. One of the more popular ones is called neighbor joining, or NJ trees. Another one is called UPGMA. You can still find these, and they're applicable in some instances. Okay, so the progressive method uses a best pairwise alignment as a seed and then adds sequences. There are some heuristics involved, shortcuts. First, the closest pair of sequence provides the most information about the true alignment. That's an assumption here. This is called a greedy assumption. It means we start at that closest pair of sequences and assume that's the best starting place. Another assumption or shortcut we take in the true progressive method is that once we have a sequence in our alignment, we never go back and revisit it. So remember, if we go back 2 slides to the summary of this approach, we select a seed, then we add the next closest sequence, then we add the next closest sequence. We are adding information to our alignment, but we never go back and revisit what that new information does to our alignment. Does it make it better? Does it make it worse? Does it change how we think about or how those sequences are aligned? Okay, some of the drawbacks. Because we never revisit the alignments, any errors that we make in the early stages are carried through to the final alignment. This leads to a fairly poor performance for distantly related sequences. And because we're taking shortcuts, because we're using a greedy approach, we are not guaranteed to provide a globally optimal solution. How can we improve upon that? The progressive method is the basis for our third approach called the iterative method. An example of the iterative method that you're going to play around with for activity 17 is called muscle. The iterative method is a realignment of sequences as you add new ones. So remember, one of the major drawbacks, if we go back 1 slide, to the progressive method is errors in the early steps propagate to the final alignment because we never revisit that alignment as it grows. The iterative method, we do that. Here's an overview of the iterative method as it's seen in muscle, and the reference for that's from 2004. So muscle has been around for quite a long time. You can go check this paper out if you want all the gory details, but I've kind of summarized it here on the left side. So first, we run a progressive alignment. And in this particular case of muscle, we use something called a Kamer distance matrix. And we'll talk about Kamers a little bit later in class. But essentially, this is a distance matrix here in step 1.1. So we create a draft progressive alignment by running a progressive algorithm. So we have a distance matrix, we make a tree, here we call it tree 1, we assemble a progressive alignment, done. Now something like T coffee or Clustal W would now stop. The iterative method, however, we improve upon that progressive alignment. So we take the suboptimal tree here, tree 1, which is quite crude, and we improve it using a second distance matrix. And that second distance matrix is built using information that we learned in our first multiple sequence alignment. We then use that distance matrix to form a second tree, tree 2. That tree is arguably superior to tree 1 since we've added more information. And so we get a second multiple sequence alignment here, again using a progressive approach. But we don't stop there. We iterate again using a refinement step. So in this refinement step, we have a multiple sequence alignment here. We use this multiple sequence alignment to generate another tree. That tree is then snipped. So we delete an edge from tree 2, giving 2 subtrees. Take this tree and we snip it. Just break a branch. Delete an edge. Then we can compute the multiple sequence alignment from each of these subtrees. Then we realign those subtree alignments to see if we get a better score. That's this 3.4. And we can calculate this using the sum of pairs score that we talked about in the first approach, that SP-min score. Because now we only have 2 alignments and we can calculate those 2 alignments fairly easily. So we calculate an SP score. We say, is our SP score better or worse than the alignment before? If it's better, then we have a new multiple sequence alignment. We can go back and repeat by snipping apart the subtree again, computing subtree profiles, realigning profiles, and calculating the SP score. We continue to do this iterative refinement of our tree until we stop seeing better SP scores. Once we've minimized our SP, then we stop. So the iterative approach is based on progressive. It does several additional steps in order to improve our alignment. And in Edgar's original muscle paper from 2004, he has a good example of how T coffee, which is a progressive alignment program, and muscle treat an alignment of SH2 domains differently. SH2 domains are fairly well conserved. T coffee alignment of an SH2 domain part of a protein is on the top here, and I've colored and capitalized the residues that are in the domain that should be aligned. And you can see that T coffee is not doing a very good job of aligning these domains. Here's MGC over here over gaps. Here MGC triplet from other sequences. Does a decent job aligning the PA domains for these, but again, this sequence is out of alignment. The HYG domains are all over the place, etc. This is because T coffee has some error in the early alignment that then propagates to the end. Muscle, however, does a much better job because it uses that iterative process to check its alignment and make sure that it's scoring fairly well by the end of this process. And so a muscle alignment of these domains, you can see the MGCs are aligned, the SKE, KPA, KY, and etc. Okay, activity 17 is available on eCampus. Align this. There is a file on the Google Drive folder called supplements called act17.fa. This file contains several 16S gene sequences from various bacterial species spread across the tree of life. You're going to align these sequences to each other. So step one is open a web browser and go to the EBI tools page for multiple sequence alignment. The link is here. It has a number of different alignment algorithms. You are free to try any of them, but for this activity, we're going to focus on two. One is muscle that we just talked about. That's the iterative approach. So scroll down and choose launch muscle. You'll be using activity17.fa as your input. You can either copy and paste it in or upload it as a file. Choose output format HTML. Then click the More Options button and choose Output Tree from either first iteration or second. This is simply for you to look at what that crude output tree. Then click the Submit button. You may have to wait a few minutes for it to align, but it shouldn't take too long. Take a look at that, save it, keep the window open, whatever you prefer. You're going to then go back to that main MSA page that's linked up here and choose Launch T-Coffee. Remember, T-Coffee is the progressive alignment. Don't forget to select DNA from that first selection box so T-Coffee knows these are DNA sequences. Again, use that FA file as your input, choose output format HTML, and then click Submit. There are then two questions that you need to answer for this activity, A and B. They should be fairly straightforward. Okay, that's it for today. If you have any questions, please drop me an email. Otherwise, I will see you again in the next lecture.